In this video, I just want to give a quick overview of finding determinants by a cofactor expansion. So in the previous video, I explained determinants using permutations. But there's another way to calculate determinants using something called a cofactor expansion. And that's what I want to discuss. In fact, many books use this cofactor expansion as the definition of the determinant, and they don't talk about permutations at all. So I already wrote down the notes, but let's just go over this. So let's say that you have an n by n matrix, and you want to find its determinant. So let's say that you take a row I and column j, row I and column j, and you remove them from your matrix A. Then you end up getting an n minus 1 by n minus 1 matrix. And that matrix is called the ij minor of A. And it's in capital A sub ij. That's the ij minor. Okay? And I just did an example. So let's say that you have this matrix A, and then you take the 2, 3 minor. So that means you remove row 2 and column 3, and then you get this matrix, 1, 2, 7, 8. Okay? Now, using these minors, you can define something called a cofactor. And the ij cofactor is what you get when you take negative 1, raise it to the I plus j power, and then multiply that by the determinant of the minor, the ij minor. And I gave an example. The 2, 3 cofactor of capital A is, so I have this A sub 2, 3, this matrix, and when you take I equals 2 and j equals 3, I want to make sure this is recording. Okay. You get negative 1, and then times the determinant of that minor, you get 6 as a result. Then the theorem says that you can pick any I from 1 to n, and the determinant of A is given by this formula. It's the sum from k equals 1 to n of negative 1 to the I plus k power times A sub ik times the determinant of capital A sub ik. Okay, and that's an expansion using cofactors. The only difference is you have this A sub ik. Otherwise, you'd have the cofactor. So let's see how to find the determinant of the matrix A that we had above. So here's the formula that I wrote down for the determinant of A. Okay, and then here's the matrix A. And when you write everything out, and I encourage you to work this out, you get the determinant of A is 0. And a few notes. So in the example that I did, I used I equals 1. Right? I picked I equals 1. But it turns out, so that's cofactor expansion along the first row, along row 1. But you can use I equals 2 or 3 in the example. In other words, you can do cofactor expansion along any row. And that's implied in this theorem. The theorem says pick any I from 1 to n. So, and you're going to get the determinant of A. So, implicit in this theorem is that it doesn't matter which I you pick. Okay, just any of them from 1 to n. And then the other thing is that you can also go along the column. You can do cofactor expansion down a column instead of across a row. And the reason is because the determinant of A transpose is equal to the determinant of A. So when you take the determinant, the columns become the rows and vice versa. And since it doesn't matter which way you go about it, right, when you take the transpose and calculate the determinant across a row of A transpose, you're going to get the determinant of A. But when you take the row of A transpose, that's a column of A. And so you can go down the column of A and not just along a row of A. And when you write down the formula using the column, going down column I, you get this. And I did an example, here's an example where you have the same matrix A, but you take the cofactor expansion down column 2. And if you write down the minors and then calculate the determinants and use the formula, you get a different sum, right? You get different numbers. You get different numbers here, but you still get 0. So it's kind of surprising that it doesn't matter which row or column you pick, you get the same number when you use the formula. So for this matrix A, there are actually 6 possible ways to calculate the determinant, because there's 3 rows you can go across, and then there are 3 columns you can go down. Okay, and I didn't prove the theorem, but there's a book by Mex and Mex called Linear Algebra, and it gives a proof. It proves that the determinant using the permutations is the same as the determinant using this cofactor formula. Okay, thanks.